Oh. All right. Oh. View, seamless, view, single page. Okay. No real announcements. Let me see. We are wrapping up chapter 2 today. You know, we were only going to do like 3 sections in chapter 2. So today we're going to be working on section 2.3, dividing polynomials and the rational zero test. So then what that means is that at the end of this week, we'll be ready for exam 3 over chapter 2. It'll become available this Sunday. I think I had it scheduled for like the Sunday morning at 11 a.m. You know, for the first 7 days, you can earn maximum credit, like up to 100%, but past the due date, the highest you can earn is a 90, right? I think it's set to unlimited attempts. You know how the tests go by now, right? No update on the final, so we'll talk about that as we get closer to it. And I think the school might be closed on that Wednesday during Thanksgiving. I know we're going to meet on that Monday. Even though we did meet on that Wednesday, I mean, honestly, if you guys like wanted to start traveling early, you can. If you could just like log in, if we do meet on that Wednesday, I got to look and see how I have it scheduled. But anyway, okay. So again, today we're going to be, and as usual, if you have questions about anything, feel free to unmute yourself or type in the chat to get my attention and we can talk about it. And so for today, we're going to be working on section 2.3, dividing polynomials and the rational zero test. A few objectives. 1, learn the division algorithm. 2, use the remainder and factor theorems. And then 3, use the rational zero test. So a polynomial d of x is a factor of a polynomial f of x if there's a polynomial q of x such that f of x equals d times q. Okay. So if we say a dividend divided by our divisor, we're going to get a quotient plus some remainder over our divisor. Notice with this, if we multiply both sides by our divisor, we get our dividend equals the divisor times the quotient plus the remainder. Right? Okay, this is fine. But so basically what this kind of parallels long division, right? So the same way we do long division, we're going to be doing this, working on this technique called polynomial long division. So here we're actually use long division and synthetic division to find the quotient and remainder when this dividend is divided by this divisor. And we'll start by performing long division. Okay, let me get a copy. Let me go to select, duplicate. Then I'd like a screenshot of this. Okay. Perfect. I'm done. Okay. And again, I'll check attendance again for anybody that's kind of late. Like we missed about 2 students. I'll check again around the 15-minute mark. All right, so let's do a showcase on polynomial long division. Again, it parallels the way we do regular long division with numbers, with a few changes. So first we have our divisor, which is this. Actually, let me do this. Space. Paper. I like writing on this. Okay, so our divisor is this x plus 2. And we're doing what? Long division? Well, actually, let me do that a little bit later. Okay, so then our dividend, we have this 2x to the 4 plus x to the power of 3 minus 16x squared. Notice that x to the power of 1 is missing, so we actually need a placeholder. Okay. And then plus 18. So we need to make sure that every power is accounted for. Notice we have power of 4, power of 3, power of 2, power of 1, and power of 0. Okay. Okay, so then when we go to do our long division, we say our first term divided by our first term. So 2x to the 4 divided by x is going to be 2x to the third. And we line up our like terms. So we got a 2x to the third here. Then on a diagonal, we multiply. So 2x to the third times x is 2x to the 4. 2x to the third times 2 is 4x cubed. Now, if this were regular long division, our next step would be to subtract. So we're going to do something similar here. In order to subtract that second line, we need to distribute a negative. So this guy becomes negative, and this guy becomes negative. So now when we combine like terms, a number plus its opposite, these guys add to 0. 1 minus 4 is negative 3, x to the third. Then the next term comes down. Negative 16x squared, okay? Then, let's see. We repeat the process. So we say the first term divided by the first term. So then, negative 3x cubed divided by x is going to be a negative 3x squared. Notice I'm lining up my like terms for my results. On a diagonal, we multiply. So negative 3x squared times x is going to be a negative 3x cubed. Negative 3x squared times 2 is going to be a negative 6x squared. And then we need to distribute our negative. So this guy becomes positive, this guy becomes positive. So now when we combine like terms, a number plus its opposite, these guys add to 0. Negative 16 plus 6 is going to be negative 10 x squared. And then the next term comes down. Okay. Then we repeat the process. Negative 10x squared, so the first divided by the first. Negative 10x squared divided by x is going to be a negative 10x. That's fine. Then on a diagonal, we multiply. So that's going to give us a negative 10x squared minus 20x. Then we distribute our negative, so this becomes positive and this becomes positive. A number plus its opposite, these guys add to 0. Then that's going to be 20x. And bring down the final term. Plus 18. 20 divided by x is 20. We get 20x. And what is that? 40. Distribute our negative. So this becomes negative. This becomes negative. It looks like our result. It's like a negative 22. This is our remainder. Okay. And we can capture that up above by saying, in this case, it would be a minus 22 over x plus 2. Okay. Our remainder over our divisor. Okay. So when we did polynomial long division, we got this result. Now, because we're dividing by a linear binomial, we have this other technique that we have at our disposal, and it's called synthetic division. Okay. So with synthetic division, because we're dividing by a linear binomial, first thing is we want to put the 0 or the linear binomial in the chair. So the 0 in this case is going to be -2. So we put -2 into the chair, and then we take our coefficients, which are 2, 1, -16. I think we need a placeholder of 0. And then we get our 18. All right. We started with degree 4, so we should have 5 coefficients. 1, 2, 3, 4, 5. Okay. So this is how we set up the structure for synthetic division. So then the first number just comes down. On a diagonal, we multiply. So -2 times 2 is -4. And then vertically, we add. So 1 plus -4 is -3. -2 times -3 is a +6. Vertically, we add. Diagonal, we multiply. Vertically, we add. Diagonal, we multiply. And vertically, we add. So then the -22 serves as our remainder. Since we started with a degree 4 polynomial, at this point we have what's called the depressed equation, which means that the degree drops by 1 degree. So now we have a degree 3 polynomial. And again, this is our remainder. And I think that matches what we had on the other. Try to give it a couple more minutes to get to 15 before I check for my attendance again. Okay, so we saw a showcase on 2 different ways of doing the same thing. Obviously, synthetic division to me is easier, but we don't always have it at our disposal for use. You know, again, we can only use synthetic division if we're dividing by a linear binomial. Okay. Okay, so then we have the remainder theorem. If a polynomial f of x is divided by x minus a, then the remainder r is given by, the remainder is going to be equal to f evaluated at a. Okay. So here we're asked to find the remainder when this polynomial is divided by x minus 1. Our a being our 0, the linear binomial, in this case is going to be a 1. So if we want the remainder, we could just evaluate this when x is 1. Okay. So our remainder is going to be, in this case, it's going to be f of 1. It's going to be a 2 times 1 to the 5th power minus 4 times 1 to the 3rd power, 5 times 1 squared, 7 times 1 plus 2. Okay. So then that's 2 minus 4 plus 5 minus 7 plus 2. Okay. 4 minus 4, those add to 0. 5 minus 2 is a negative. 5 minus 7 is negative 2. Okay. And then here, given this function, they ask us to evaluate when x is 3. Now, obviously, we could just plug in. But if we apply the remainder theorem, if we do synthetic division, our remainder is going to give us f of negative 3. So in this case, I'm going to put my negative 3 in the chair. I want my coefficients, which are 1, 3, negative 5, 8, and 75. Let me see. 1, 2, 3, 4, 5 is correct. Okay. So then the first term, I'm about to check attendance in this moment. The first term just comes down, which is a 1. Then we get our negative 3. Vertically, we add, we get 0, 0, negative 5. Again, whenever we're going on a diagonal, we multiply. Whenever we go vertical, we add. So that gives us our 15. Is that 23? Negative 69. And then a 6 is our remainder. Okay. So then f of negative 3 is going to be equal to our remainder, which is 6. That's the remainder theorem. Okay. Let me check on you guys in Zoom. The remainder from our synthetic division. Okay. So then we have the factor theorem. A polynomial f of x has x minus a as a factor if and only if f of a equals 0. Right? So this is like an application of the remainder theorem. If our remainder is 0, then we're saying that x minus a is a factor of our polynomial. Okay. Let's see. So given that 2 is a 0, this function, we're asked to solve this polynomial equation. So we're kind of fortunate because they already gave us 1, 0. A lot of times when solving polynomial equations, the hardest part is finding that first 0, right? So in this example, they gave us our first 0. So let's just confirm that 2 is indeed a 0. So we can do, if we do synthetic division with 2 in the chair, our remainder should be 0. Okay. Now our coefficients, let me see, 1, 2, 3, 4, okay. So we have 3, 2, negative 19, and 6. Now the 3 comes down. On the diagonal, we multiply, we get 6. Vertically, we add, we get what, 8? And that's 16, that's negative 3, negative 6. Indeed, we got a remainder of 0. Okay. So then we started with degree 3. At this point, our equation is now a degree 2. And I think we can factor this guy. We're looking for two numbers that multiply to give us -9 and add to give us 8 are going to be -1 and 9. Okay, so I'm a fan of using the box method for factoring. You might be familiar with like the X method. There it is. Okay. So with this technique, in the upper left-hand corner goes our leading term, which is this 3x squared. In the bottom right goes our constant, which is -3. And then on the off diagonal, we're rewriting the 8 using the two numbers that we found. So we had a 9x and a -x. Okay. So then now to go factor, if we look at these two on the top, we ask ourselves, well, what do these two have in common? It's like we could factor out a 3x from both of those guys. Okay. What about the two on the bottom? What can we factor out of these two? Looks like a -1. Okay. What about the two on the left? We can, I think they have the greatest common factor is an x. And the two on the right, the greatest common factor is 3. Okay. So then our claim is that this quadratic factors into 3x minus 1 times x plus 3. And then we also want to incorporate the 2 that we were given. In order for 2 to be a 0, the linear factor would be what? X minus 2. So this is the completely factored form of the polynomial equation. Okay. So now we have 2 or more things that multiply to give us 0. Long story short, we set each thing to 0 and solve. And when we do this, I think we're going to get what? -3. We get a 1 by 3. We get 2. Okay. And let's just do a quick check using our calculator. Okay, so if I go to my y equals, we have 3x to the power of 3 plus 2x squared minus 19x plus 6. Okay. So then we want to evaluate this at these 3 different x values. So I'm going to just call in the function we just inserted. And let's evaluate it first when x is -3. The result should be 0. Let's evaluate it when x is a 1 by 3. Or 1/3. We get our 0. And when let's evaluate it when x is 2. We should get 0. Okay. So we confirm these 3 results are indeed our 0 of our polynomial. Okay. Okay, let's keep going. let me see. I'm going to leave this one as an exercise for you. I think we can do that. I think we got time. 10 minutes, 35. I think we have time. Let's go. Actually, let me come back to this one. This is the last, I think my earlier classes, we didn't get a chance to work through the example. I'd like to get into this one. So here we have the rational zero test. If f is a polynomial function with integer coefficients, and our leading coefficient and our constant term are not both zero, and p over q is a rational number in lowest terms, that is a zero of our function, then p is going to be a factor of the constant term, and q is going to be a factor of the leading coefficient. So what this test will do for us, this is called the rational zero test, and what it does, it lists out all possible rational zeros of our polynomial at hand. What we mentioned just a moment ago, we were saying that one of the challenges of solving polynomial equations is finding that first zero. So what the rational zero test does is gives us a list of possible rational zeros to consider. It kind of narrows down the list for us. So we're not just guessing a check and pulling numbers out of thin air. We actually we can generate a list to start with, right? To find those first couple of zeros. So here we're asked to find all the rational zeros of this polynomial, right? So again, the challenge is, well, what's the first zero? So we can use the rational zero test. So the rational zero test, our P is basically going to be our P over Q, where P are all the factors of our constant term. Okay, so our constant term in this case is just -3. So the factors of 3 are going to be what? Plus or minus 1 and plus or minus 3. Okay. And then our Q comes from the factors of our leading coefficient. In this case, that's 2. So the factors of 2 are going to be plus or minus 1 and plus or minus 2. Right? So then if we do all combinations of red over each of the blues, we get the following list that we can generate. So 1 over 1 is 1. 3 over 1 is 3. And then 1 over 2 is a half. 3 over 2 is 3 halves, right? So what we're saying is, if this polynomial has any rational zeros, those rational zeros are in this list. Okay? So then we can use this list to kind of pretty much guess and check for some rational zeros, right? So let's start off with 1. If we want to test if 1 is a rational zero, when we do synthetic division, our remainder should be 0. Okay? So if we put 1 in a chair, our coefficients are going to be 2, 5, -4, and -3. I don't think we need any placeholders. I think we're good as far as that's concerned. Okay. So again, the first term just comes down. 1 times 2 is 2, plus 5 is 7, times 1 is 7, plus -4 is 3, times 1 is 3, plus -3 gives us our 0. So that confirms that 1 is one of our zeros. So we found 1 0. So then, since we started with a degree 3, now we're at a degree 2 polynomial. Maybe we can factor this. We're looking for two numbers that multiply to give us 6. A times C, 2 times 3. We're looking for two numbers that multiply to give us 6 and add to give us 7, and I think that's just going to be 1 and 6. Okay, so if we use the box method of factoring, that's right. Okay. So in the upper left-hand corner goes our leading term, which is 2x squared. The bottom right is our constant, which is 3. And then the off diagonal, we're rewriting a 7x using the two numbers we just found. So I'm going to put my 6x here and my 1x here. So then we consider the GCFs. If we look at the two on top, what's the greatest common factor? It looks like they both share an x. If we look at the two on the bottom, what's the greatest common factor? It looks like it's a 3. If we look at the two on the left, the greatest common factor looks like 2x. And the greatest common factor of the two on the right looks like it's 1. So our claim is that this 2x squared factors into 2x plus 1 times x plus 3. And then not to mention the one that we already found, the 0 that we already found was, that's going to be x minus 1. Okay. So then we we have two more things that multiply to give us 0 from the zero factor property. We set each factor to 0 and solve. So then we get x equals, looks like it's a -3. Notice it's in our list. A -1/2. That's also in our list, and 1. Let me check if you guys in Zoom. I think you're okay. And then we can check this here. Give me just a moment. Okay. Let's see. So the original we have is 2x to the power of 3 plus 5x squared minus 4x minus 3. Okay. And then we want to evaluate this function when x is -3. We should get 0. We want to evaluate this when x is a -1/2 and when x is 1. Okay. So notice that these three values of x all gave us 0, so we can be confident in this resource. Okay, so find all the rational zeros. P are going to be the factors of the constant term. Q are going to be the factors of the leading coefficient. So we get these possible rational zeros. These are not the actual rational zeros. We're saying if our polynomial has rational zeros or somewhere in this list. So we tested one. We got lucky. We found the first 0 quickly. So then it gave us our depressed equation that we just factored, solved. We got the same result. Okay. Let me take some time to actually go through the one that we skipped, and then we'll call it a day. I'll just use my notes. It says the combined petroleum consumption in quads by a group of the most economically developed countries in the world from 96 to 2011 can be modeled by this function, where x equals 0 represents 1996, x equals 1 represents 97, and so on. The model indicates that after 5 years, 238 quads of petroleum were consumed in 2001. Find another year between 2001 and 2011 when the model indicates that 238 quads of petroleum were consumed. Right, so we want to see when is this function, at what years is this function equal to 238? So we basically set this equal to 238 and solve. Sure about that. Let me get a blank page. Okay. And let me get a copy of okay. So we want to set this guy equal to 238 and solve. Okay. So if we say 0.021 x to the power of 3 minus 0.973 x squared plus 11.347. I think there's supposed to be an x there. I think that's a typo. Plus 202.2965. We want to set that equal to, I think it was 238. 238. So if we subtract 238 from both sides and set it equal to 0, we'll get, I guess I'll just copy and paste. So then 202.296 minus 238 negative, what does that feel off? 202.296. Oh, because it's not supposed to be 296. It's supposed to be 965. Let me fix that. Okay. So here we get 35.035 equal to 0. Now, we got that 1, 0 is supposed to be when x is 5. So we can confirm that with synthetic division. If we take our coefficients, 0, 0, 0.021, negative 0.973, 11.347, negative 35.035. If we do synthetic division where x is 5, again, the first number just comes down. Um, 105, 0105. Hey Google, what's 0.021 times 5?
0. I don't understand. 1 times 5 is 0.105.
Forget it. I'll just do it here. Point 0.021 times 5. So then 105. Then we want to take that answer and what, say minus 0.973. So minus 0.973. 868. Then we want to say the answer times 5. 4.34. And then we're going to say that answer plus 11.347. Times 5 is going to be 35.035. So we confirm that the 5 is indeed a 0. In other words, in the original, it gives us 138. So then we want to solve this guy, right? Well, since we started with a degree 3, at this point, we're at a degree 2. And we can actually use the quadratic formula. Quadratic formula, the negative boy couldn't decide to go to the radical house because he was square, so he missed out on 4 awesome chicks. It was all over by 2 a.m. Again, our A is here, our B is here, and our C is here. So then negative is going to be 0.868 plus or minus that 0.868 squared minus 4. Our A is 0.021 and our C is 7.007. I'm going to say all of that divided by 2 times our A. Okay. And then we can use a calculator for this. Okay. So then we have 0.868. Let me close off the numerator or open up the numerator. 0.868. Let's go ahead and do our minus the square root. We got 0.868 squared minus 4 times 0.021. That's not a 1. Times 7.007. This closes off the square root. This closes off the numerator. Divided by 2 times 0.021. 11 years, right? So one result that we get is when x is 11. And then if we change the minus to a plus, right, we get 30.3 bar. But they wanted the years from 2001 to 2011. So if 0 is the year 96, 10 would be 2005, so 2006, and then 2007. So when x is 11, we get the year 2007. 30 goes outside the range. 30 is too large. Let's undo. Are there any burning questions for me before we go our separate ways? Any burning questions? Going once, going twice. Forever hold your P's and R's. Okay. All right, so that actually brings us to the end of the section. As far as announcements, on Wednesday, we're gonna do more practice for this. We'll go through as many homework questions together as we can. And then we can anticipate exam 2 to become available this Sunday. You can earn max credit for 7 days. After the 7th day, which is past the due date, the highest you can earn is a 90. Again, if there aren't any burning questions, we're going to go ahead and end the session here. And from one beautiful mind to another, enjoy the rest of your day, gentlemen. See you Wednesday, same time, same place. Take care. Peace.